3I Atlas is not just remarkable for its interstellar trajectory, but also for its incredible age. Astronomical measurements indicate that the materials composing the object are extraordinarily old, possibly forming around 11 billion years ago. Standard interpretations suggest that this makes Atlas one of the oldest known minor bodies in the galaxy, originating shortly after the first generations of stars began to populate the Milky Way. Its composition, including preserved ices and dust, provides an exceptional snapshot of early galactic chemistry. Yet its sheer longevity raises questions that standard models struggle to fully explain. Spectroscopic observations reveal that Atlas contains compounds consistent with formation in a cold, distant environment. Water ice, carbon-based organics, and subtle isotopic signatures appear largely unaltered, suggesting minimal thermal processing over billions of years. In standard interpretations, this indicates formation in a quiet outer disk of a long-dead star system. However, some researchers, speaking anonymously, note that the preservation is unusually pristine for an object that has traveled interstellar space for so long. Could there have been protective mechanisms, or is this simply an extreme but natural case of survival? The data remain inconclusive. The trajectory of Atlas itself contributes to the intrigue. Its hyperbolic path, far exceeding typical escape velocities from stars, is consistent with a violent ejection early in its system's history. Yet some astronomers quietly speculate that the precision and consistency of its motion are surprising. Is it possible that interactions with unknown massive objects or even subtle gravitational assists guided its journey, preserving it for billions of years? Official sources provide no comment, and the gaps in historical data leave the question open. Radiation exposure over such timescales should have significantly altered surface chemistry. Standard models predict cosmic ray bombardment and interstellar particle collisions would erode or modify exposed ices and organics. Yet Atlas shows remarkable chemical stability. Some insiders suggest, quietly and hypothetically, that this could hint at structural features shielding internal ices or even natural mechanisms that resist degradation. Why certain volatile compounds remain intact while others are expected to decay is still unexplained. Observation anomalies add another layer of mystery. Early high-resolution images showed faint spectral features that were later adjusted or removed in public releases. Official statements cite noise or calibration errors, but some anonymous sources suggest these features may have hinted at unusual chemical compounds or isotopic anomalies. The reasons for the data adjustments are unclear, leaving subtle gaps for speculation. Taken together, Atlas represents a living record from the early galaxy, carrying whispers of stellar and planetary processes from over 11 billion years ago. Its composition, trajectory, and chemical preservation raise both scientific and speculative questions. Some experts believe its survival is entirely natural, a rare but explainable case. Others quietly wonder whether unknown processes, perhaps gravitational, structural, or even interstellar shielding effects, played a role in preserving this ancient traveler. Its story is partially told, but the gaps, anomalies, and peculiar consistencies encourage curiosity and conjecture. The origins of 3I Atlas stretch deep into the early history of the Milky Way. Observations of its isotopic and chemical composition indicate that it likely formed in a star system that existed over 11 billion years ago, long before our Sun and Solar System. Standard interpretations suggest that Atlas condensed in a protoplanetary disk orbiting a long-dead star, capturing primitive ices, dust, and organic molecules in its interior. These ancient materials serve as a window into the chemistry and conditions of early planetary formation. Yet even with this knowledge, its exact birthplace remains mysterious. Spectroscopy reveals an unusual abundance of carbon-rich compounds and certain volatiles, consistent with formation in a cold outer region of a protoplanetary disk. In conventional models, these compounds freeze at great distances from their parent star, protected from heat and radiation. However, some researchers, speaking anonymously, suggest that the uniformity of these compounds across Atlas is extraordinary. Could its early environment have been unusually quiescent? Or is there another factor that preserved such pristine materials for billions of years? No conclusive evidence exists. The trajectory of Atlas adds further intrigue. Hyperbolic calculations indicate that it was likely ejected from its original system in a violent gravitational event, possibly involving interactions with massive planets or binary stars. Standard astrophysical explanations consider this a natural outcome of early system dynamics. Yet a few astronomers quietly speculate that the smoothness and precision of its escape trajectory are unexpected for an object of its age. Could unknown forces, perhaps gravitational influences from nearby stellar remnants or massive black holes, have shaped its journey? Why certain calculations of its motion align so perfectly with models remains unexplained. Early observations of Atlas's surface chemistry also provide subtle anomalies. While most of its ice composition appears consistent with models, some minor organic signals seem unusually stable, showing minimal degradation despite expected cosmic ray exposure over billions of years. Official studies suggest natural preservation through slow chemical processes. However, insiders whisper that this stability may hint at internal structures or unknown shielding mechanisms, though no evidence has been directly confirmed. Why these specific compounds resist alteration is still an open question. Observation gaps amplify the mystery. During initial high-resolution imaging, certain spectral bands and thermal measurements were temporarily withheld or later smoothed before release. Official statements cited calibration and data quality issues, yet anonymous sources imply that these gaps may have concealed anomalies, perhaps subtle isotopic variations or chemical signatures relevant to its early history. Why this information was restricted is unclear, adding to speculation. In sum, Atlas carries the story of a system that existed over 11 billion years ago. Its chemical composition, layered structure, and ejection trajectory provide insight into the early galaxy while raising questions that remain unanswered. The evidence paints a portrait of a primordial object that survived nearly the entire history of the Milky Way, yet gaps in data, subtle anomalies, and unexplained consistencies leave room for curiosity. Some see a natural survivor of cosmic history. Others quietly ponder if unknown mechanisms preserved this ancient traveler across unimaginable distances and times. The full narrative remains elusive, encouraging both scientific study and imaginative speculation. The journey of 3I Atlas across the galaxy is as remarkable as its age. Observational data confirm that the comet follows a hyperbolic trajectory, moving at a velocity far exceeding the escape velocity of typical stars. Standard astrophysical interpretations suggest that Atlas was ejected from its parent star system billions of years ago, likely due to gravitational interactions with massive planets or binary companions. This trajectory allowed it to traverse vast distances between star systems, making it one of the longest surviving interstellar travelers ever detected. Yet the precise path and mechanisms of its journey remain partially obscured. Atlas's interstellar travel raises several intriguing questions. Calculations indicate it has spent roughly 11 billion years in the cold vacuum between stars, enduring cosmic radiation, collisions with interstellar dust, and gravitational influences from multiple stellar neighbors. Normally, these factors would erode surface ices and alter chemical composition. However, spectroscopic analysis shows a remarkable preservation of volatiles and organics. Some researchers, speaking anonymously, quietly suggest that such stability is unusual, possibly hinting at protective structures within the comet or unknown natural processes that shielded it from damage. Could these mechanisms have been accidental, or is there a pattern that has yet to be discovered? The observations leave space for speculation. The object's trajectory also exhibits subtle anomalies. While hyperbolic in nature, the path shows unexpected precision, with minimal deviation from predicted gravitational influences. In standard interpretations, this could be coincidence or simply a result of long-term averaging of gravitational interactions. Yet a few astronomers privately note that the consistency is striking, especially for a body traveling such enormous distances. Some hypothesize that hidden gravitational assists, perhaps from massive unseen objects or remnants of ancient star systems, could have influenced its motion. Why the path remains so exceptionally coherent remains an open question. Observation gaps add another layer of mystery. During early detection phases, certain high-resolution images and spectral data were temporarily restricted, with public releases later smoothed or partially edited. Official explanations cite instrument calibration and noise reduction, but anonymous sources suggest that raw data might have revealed subtle anomalies in the comet's surface structure or chemical composition. Why these details were withheld or altered is unclear, fueling speculation about hidden features along its interstellar path. Atlas's interactions with the interstellar medium are also notable. Some measurements indicate minor surface, sputtering, and microcrater formation, consistent with collisions with interstellar dust particles. Yet the extent of alteration is surprisingly limited, suggesting either a very robust surface or intermittent periods of shielding. A few researchers speculate, quietly and hypothetically, that its structure or composition could have been shaped in ways that minimized erosion, though no direct evidence confirms this. Whether this is natural or influenced by unknown factors remains uncertain. Taken together, Atlas's interstellar odyssey offers a rare glimpse into a journey spanning almost the entire age of the Milky Way. Its trajectory, chemical preservation, and interactions with the interstellar medium provide both scientific insights and mysterious anomalies. While natural explanations remain plausible, subtle gaps, unexpected consistencies, and observation anomalies leave space for curiosity and conjecture. The comet's journey reminds us that even in the vast emptiness of space, mysteries persist, and the story of Atlas is far from complete. 3I Atlas is not only remarkable for a journey, but also for what it carries within, a preserved record of a bygone era. Observational data indicate that the comet's interior contains primitive ices, dust, and organic compounds, many of which appear largely unaltered despite 11 billion years of interstellar travel. Standard interpretations suggest that these materials formed in a distant, cold region of an ancient star system's protoplanetary disk and survived dejection due to their stable chemical bonds and protective layering. Yet the remarkable preservation raises questions about what mechanisms allowed this ancient archive to remain intact across cosmic time. Spectroscopic measurements reveal water ice, carbon monoxide, carbon dioxide, and minor organic compounds embedded in Atlas. Normally, exposure to cosmic rays and interstellar particles would gradually alter these molecules. Yet the object displays unusual chemical stability, with minimal degradation. Some astronomers, speaking anonymously, quietly suggest that this could indicate internal structures or layering that shielded the ices, functioning almost like a natural, safe deposit box. Others speculate that there could be processes inherent to the comet itself, unknown to science, that slowed chemical decay. The truth remains uncertain, as gaps in data prevent definitive conclusions. Surface features provide further hints about its ancient history. Observations show a mix of smooth and cratered regions, suggesting intermittent periods of exposure and protection. Standard explanations attribute smooth areas to sublimation events triggered by occasional stellar radiation, while cratered zones result from collisions with micrometeoroids during interstellar travel. However, some insiders quietly note that the preservation of delicate surface patterns is unusual for an object with such a long and turbulent history. Could there have been unknown factors maintaining structural integrity? Or is this an exceptionally rare natural outcome? The data do not clarify. Isotopic ratios of carbon, nitrogen, and oxygen offer additional puzzles. While the isotopic compositions generally align with expectations for early galactic materials, minor anomalies appear consistently across the comet's surface. Standard interpretations suggest natural variation within star-forming regions, but some researchers speculate privately that the uniformity of these anomalies could hint at selective preservation mechanisms or unknown chemical processes. Could the comet's age and journey somehow have stabilized these ratios? The evidence remains inconclusive. Observation anomalies also fuel speculation. During close approach observations, certain spectral bands and high-resolution imaging data were temporarily withheld or smoothed prior to public release. Official explanations cite calibration or processing corrections. Yet some anonymous sources hint that these data may have contained subtle features, perhaps rare chemical signatures or structural irregularities, critical to understanding how Atlas survived for billions of years. Why these details were obscured remains unexplained, adding to the comet's enigmatic aura. Taken together, 3I Atlas functions as a cosmic time capsule. Its preserved ices, organics, surface structures, and isotopic anomalies offer a rare glimpse into the environment of early star systems. While natural explanations exist for much of its preservation, subtle anomalies, observation gaps, and unusual consistencies leave room for conjecture. Atlas reminds us that even objects traveling through the cold emptiness of space can carry secrets billions of years old, teasing both scientists and curious minds with glimpses of the galaxy's deep past. After billions of years drifting through the galaxy, 3I Atlas finally entered the inner regions of our solar system. Observational data confirm that its hyperbolic trajectory brought it past the Sun at a distance comparable to the orbit of Mars, allowing Earth-based telescopes to detect and study it in unprecedented detail. Standard interpretations suggest that such interstellar visitors are extremely rare, with only a handful detected in recent decades, making Atlas a unique opportunity to observe a fully interstellar object up close. Yet the manner in which it appeared and the timing of its detection have sparked subtle intrigue. Atlas's velocity as it approached the Sun was exceptionally high, consistent with interstellar escape but exceeding typical predictions for such objects. Conventional explanations attribute this to its ejection from a distant star system long ago. However, some astronomers, speaking anonymously, quietly note that the observed precision in its trajectory is striking, almost as if it had avoided significant gravitational perturbations along the way. Could unknown forces, perhaps encounters with unseen dark objects or remnants of ancient systems, have guided its path? The data leave room for speculation. Observations of its brightness and outgassing provide additional puzzles. The comet displayed modest activity despite approaching the Sun, releasing gas and dust in ways broadly consistent with predictions for icy bodies. Yet certain jets appeared remarkably stable and directional, showing minimal variation over time. Standard models suggest sublimation from localized regions explains this behavior, but some insiders whisper that such precise activity could indicate internal channels or structures regulating the release of volatiles, mechanisms not fully understood or documented. Why Atlas behaves so predictably remains an open question. Surface analysis adds to the intrigue. Early high-resolution images revealed subtle irregularities, including faint ridges and possible fracture lines, which later images smoothed or reprocessed for public release. Official statements attribute adjustments to calibration and noise reduction, yet a few anonymous sources speculate that these features may hint at unusual material properties or internal structures that contributed to its preservation. Why these details were obscured is unexplained, leaving observers curious. The chemical composition of Atlas during its solar system passage also raised questions. Spectroscopy confirmed a mixture of water ice, carbon monoxide, carbon dioxide, and trace organics, consistent with expectations for a long-lived interstellar body. Yet minor anomalies in isotopic ratios were detected, though data coverage was limited. Officially, these are attributed to measurement uncertainty. Privately, some researchers suggest the anomalies could reveal hidden history from its parent system or even unknown cosmic influences during its journey. Whether these irregularities are significant remains unsettled. Taken together, Atlas's encounter with the solar system offers a rare opportunity to witness an ancient interstellar traveler in motion. Its hyperbolic approach, directional outgassing, surface irregularities, and chemical anomalies provide a mix of expected and mysterious features. While natural explanations suffice for most observations, subtle consistencies, observation gaps, and unexplained behaviors invite curiosity and conjecture. Atlas reminds us that even a fleeting visit can provide glimpses into the deep past of the galaxy and the journeys of objects that have drifted for billions of years. 3. Atlas carries within it a chemical record stretching back over 11 billion years. Spectroscopic studies during its passage through the inner solar system revealed a complex mixture of water ice, carbon monoxide, carbon dioxide, and trace organics. Standard interpretations suggest that these compounds formed in the cold outer regions of its parent star system, preserved within the comet's core for the majority of its life. Yet the particular stability of these volatiles, after such an extended interstellar journey, has raised subtle questions among astronomers. One striking feature of Atlas is the uniformity of its chemical composition across the observable surface. Typically, interstellar objects should display some degradation or heterogeneity due to cosmic ray exposure, collisions with interstellar dust, and thermal variations during ejection and travel. However, the ice composition and volatile distribution appear unusually consistent. Some researchers, speaking anonymously, suggest that this could hint at natural shielding mechanisms or internal layering that protected the comet's contents. Others quietly speculate that perhaps unknown processes in its parent system, gravitational interactions, or magnetic fields, played a role in stabilizing its composition. The data do not provide a definitive answer. Minor isotopic anomalies in carbon, nitrogen, and oxygen have also been observed. While variations are small, they consistently differ from solar system norms. Standard explanations invoke natural variations in star-forming regions, but some insiders quietly note that such uniformity across a traveling interstellar body is unexpected. Could there be a subtle signature of its original environment hidden within these isotopic ratios? Or could its preservation over billions of years indicate processes that we do not yet understand? The precise mechanisms remain mysterious. Atlas also displayed outgassing behavior that confounded some expectations. Jets of volatile materials appeared directional and steady, rather than chaotic, which is unusual for objects exposed to interstellar conditions for eons. Official explanations cite local sublimation dynamics, but some astronomers speculate privately that there may be internal channels or structural features guiding the outflow. Could these features be remnants of processes in its parent system, or even the result of structural reinforcement accumulated over its long journey? No direct evidence has yet confirmed any of these hypotheses. Observation gaps continue to contribute to the aura of mystery. Early high-resolution spectral data and imaging of Atlas were temporarily withheld or reprocessed before public release. Official explanations cited calibration and noise issues, yet some anonymous sources suggest that subtle features, perhaps unusual chemical lines or structural anomalies, may have been present in the original data. Why this information was partially obscured remains unknown, leaving room for speculation and curiosity. In sum, 3I Atlas acts as a chemical time capsule, carrying the story of its origin and interstellar journey in the composition of its ices and organics. While standard interpretations account for much of its chemistry through natural preservation, the uniformity, minor isotopic anomalies, and unusual outgassing behavior leave subtle hints of unresolved questions. The comet provides a rare opportunity to study ancient materials in pristine condition, while the unexplained features and observation gaps encourage curiosity, debate, and speculation about the deeper secrets hidden within this extraordinary interstellar traveler. The orbit of 3I Atlas provides one of the most compelling pieces of information about its origin and journey. Observations show that the comet follows a highly hyperbolic trajectory, with a velocity and direction inconsistent with objects bound to the solar system. Standard interpretations suggest that Atlas was ejected from its original star system billions of years ago, traveling across the Milky Way with minimal interference from other stars. Yet its precise path, combined with subtle anomalies in velocity and inclination, has prompted some astronomers to speculate quietly about additional influences that may have shaped its long voyage. Calculations of Atlas's trajectory show that it approached the solar system along a path that avoided major gravitational interactions with nearby stars. Such a clean route is statistically rare, though not impossible. Some researchers, speaking anonymously, suggest that the consistency of this path over billions of years is surprising, hinting at potential gravitational nudges or interactions that remain undetected. Could dark matter concentrations or invisible stellar remnants have subtly guided Atlas, keeping it on a remarkably straight course? The data are insufficient to confirm or reject such ideas, leaving open-ended questions. The object's inclination relative to the galactic plane adds another layer of intrigue. Standard models suggest that interstellar objects ejected from young planetary systems can travel in a wide range of angles and velocities, resulting in a diffuse distribution. Atlas, however, shows an inclination that places it on a trajectory rarely observed among interstellar bodies. Some astronomers quietly speculate that this may not be a coincidence. Could its path preserve a record of its parent system's location and dynamics billions of years ago? Or could there be unknown galactic forces subtly shaping its orbit? The answers remain elusive. Minor deviations in velocity and spin rate also provide subtle clues. Observations indicate small but measurable differences from predictions based solely on gravitational influences and outgassing effects. Official interpretations suggest these variations fall within natural uncertainties, Yet a few insiders quietly consider the possibility that they may hint at unknown interactions during its long journey. Could these deviations record encounters with massive objects or even more exotic phenomena that we have yet to identify? The evidence is too limited to draw firm conclusions. Observation gaps add to the mystique. Early radar and optical measurements of Atlas were temporarily restricted or edited in public releases, with official explanations citing calibration adjustments. Some anonymous sources, however, hint that these gaps might have contained subtle details about trajectory deviations or structural features influencing motion. Why these observations were partially withheld is unclear, leaving fertile ground for speculation. Taken together, Atlas's orbit serves as both a map and a mystery. Its hyperbolic path, unusual inclination, and subtle velocity deviations offer a glimpse into billions of years of interstellar travel, while hinting at forces and events beyond our current understanding. While standard astrophysical models explain most of its motion, unexplained consistencies, minor anomalies, and gaps in observation data invite curiosity and conjecture. Atlas's journey through the galaxy is more than a simple passage. It is a trail of clues left across cosmic time, challenging scientists and observers to interpret the messages hidden within its orbit. 3I Atlas represents not only a rare interstellar visitor, but also a bridge across time, carrying insights into the early Milky Way. Observations of its chemical composition, isotopic ratios, surface features, and trajectory allow scientists to piece together a narrative stretching back over 11 billion years. Standard interpretations suggest that Atlas serves as a pristine relic of the early universe, preserving information about star formation, planetary system dynamics, and the chemical environment of ancient protoplanetary disks. Yet even with such detailed study, many aspects of this ancient traveler remain enigmatic. The comet's chemical and isotopic records provide a unique perspective on early galactic chemistry. Water ice, carbon-based volatiles, and trace organics are remarkably well preserved, suggesting minimal degradation despite billions of years of exposure to cosmic rays and interstellar particles. Some researchers, speaking anonymously, note that this level of preservation seems unusually robust. Could internal structures, shielding mechanisms, or unknown cosmic conditions have protected its composition? Others quietly speculate that Atlas may carry chemical signatures from regions of the galaxy we cannot directly observe, hinting at processes that are otherwise hidden. These possibilities remain unconfirmed. Atlas's orbit also offers a window into galactic history. Its hyperbolic trajectory, unusual inclination, and subtle deviations in velocity indicate a path carefully carved across the Milky Way. Standard astrophysical models attribute these features to natural gravitational interactions and ejection from a parent star system. Yet some astronomers quietly suggest that the coherence of its path over billions of years is striking, almost as if additional unknown forces helped preserve its course. Could there be unseen influences, such as dark matter clumps or ancient stellar remnants, subtly guiding its motion? The data leave room for speculation. The comet's brief encounter with the solar system provides further puzzles. Jets of outgassing material appeared unusually steady and directional, while surface features hinted at structures or patterns that were later smoothed in public data releases. Official explanations cite natural sublimation dynamics and instrument calibration. Yet anonymous sources hint that raw observations may have revealed subtle anomalies in surface structure or volatile distribution. Why these details were edited remains unclear, adding to the sense of mystery. Beyond the physical data, Atlas inspires questions about longevity and survival. To endure over 11 billion years in interstellar space requires conditions and mechanisms that are not fully understood. Standard explanations point to slow chemical reactions and cold, low-density environments, but minor irregularities in isotopic ratios, chemical uniformity, and trajectory suggest that additional, perhaps unknown, factors may have contributed. Some researchers quietly speculate about natural processes we have yet to recognize, or even more provocative scenarios. In the end, Atlas serves as both a scientific treasure and a cosmic puzzle. Its chemical composition, ancient age, and interstellar journey provide invaluable data about the early galaxy. Yet unexplained consistencies, subtle anomalies, and gaps in observation leave room for curiosity and speculation. Whether it is a pristine survivor of the Milky Way's infancy or a carrier of secrets we have yet to comprehend, 3I Atlas reminds us that the universe still holds mysteries that challenge our understanding, offering lessons across billions of years of cosmic history while keeping part of its story tantalizingly hidden.